Camps on everyone. Let's start off. Great. So last time we started with the thermodynamics first law, dq is equal to du plus dw. And be careful with the sign convention here. It's little different from chemistry. So whenever you think about sign convention, think about a heat engine. So heat engine expects you're supposed to give heat to the engine. So that's positive. If the heat gives you the engine, that is not what you want. So that's negative. Work done by the system is positive and work done on the system is negative. Right. So when then yeah, and work done is what? Like area under the PV graph. And if you're going from left to right, it's a positive work. And if you're going from right to left, it is negative. And in a cyclic process, the area enclosed by the curve is the work done. And clockwise is your positive work and anti-clockwise is your negative work. So this was all the stuff that we did. Yeah, just give me a minute. I just kicked out all the people whose cams are not on. Great. So let's go ahead with a question. So, and this was one question we did. Let's do one more easy one and then we will go ahead. A to B, B to C, C to D, D to E, E to C, and like this. This is V naught. This is your 3V naught. The center is 2V naught. V naught, 2P naught, and 3P naught. There. So this is your PV graph. Find work done in the process A, B, C, A, and find work done in the process A, B, C, D, E, C, and back to A. Get them both. Easy question. Just get this thing. You have to just find the work done. So it's a cyclic process, so area enclosed by the curve.
So it is work done by the gas or on the gas.
Work done. That's it. They won't say anything more in physics. So whatever it is, find the work done in the process ABC. Yeah, done. What is work done by the gas? Work done by the gas. Work done in a process. Done. It's a easy one. Hope everyone has got that. Let's see. Straightforward. So you want to find the work done in A, B, C, A. So you just need to find the area A, B, C, A. So just find this area, the green shaded one, which is half into the base will be 2V naught and the height will be P naught. This process is going which way? It is going anti-clockwise, so it is negative. So minus P naught, V naught. The signs are important. And what about the work done in the whole process? If you go A, B, C, right? A, if you see the upper cycle is this will be positive work, positive P naught, V naught. This will be negative work, negative P naught, V naught. So I'm asking you the total work done. A, B, C, D, E, C, A is 0. Easy. Clear with this? So there's nothing there. It is just about areas and be careful with the signs. If you see the upper one is going clockwise, the bottom one is going anti-clockwise. So both are opposite signs. The total work done is not 2 P naught D naught, it is 0. Next one. We have a TV graph. We got a triangle like this. This is A, B, and C. At this particular point, the temperature is 300 Kelvin. Here it is 400 Kelvin. A total of 1000 joules heat is withdrawn from a gas in a complete cycle. Meaning in this entire process, you have removed 1000 joules of heat. Right? So find work done in the process B to C. There's no other information here. It's a TV graph. Let's see how you handle this. Again, if you see, I'm just playing with the thermodynamics first law. We are still not doing any work done process and all that stuff. So anyone not clear with the question, please ask me. So we got a TV graph that AB is passing through the origin. AC is vertical. BC, I don't know what it is. Only B ka temperature and A ka temperature is given, and there is no other information, no volume, nothing is given. There is one thing given though. In this entire ABCA, you have removed 1000 joules of heat from the system. Then what is the work done from B to C? Think. Take a minute or two. Anyone confused with anything, please ask. Hmm. Hari, that is wrong. No, nothing is given, Ishma. Number of moles, what kind of gas. You don't need actually. Hmm. Think another 30, 40 seconds, then I'll give you a hint and then I'll give another minute. Don't try to see each process, try to see the whole thing. Get something from there. Let me ask you this. If you start from A and come back to A, what is the delta U in this full cycle? Here, area. In the full cycle, what is delta U? Zero, isn't it? Internal energy is a state function. So in the entire process, delta U is zero. So can I say like this? In the entire process, the total heat, delta Q, delta U plus delta work done. So this is zero. So in the work done in the cycle A, B, C, A is actually minus 1000. So A to B, B to C, C to A, the work done is minus 1000. Now I want you to find the work only from B to C. I didn't ask you for the work done in the cycle. Now can you try? You got the idea? In a cyclic process, delta U is zero. So that means in a full cycle, the net heat must be equal to the net work done. 500. Hmm. Might need the number of moles, maybe. Think you will need number of moles. It's take number of moles as one. You need number of moles. I think that the reason Ishman is asking. Number of moles is one. You will need it. Now see, maybe that is the reason you guys are stuck. Let's see. Then it is done. So how do we do this? So in the full cycle, delta Q is equal to delta U plus work done. This is your rating for the full cycle. Delta U is zero. It's a state function. And this will be minus 1000 joules. This is the work done. So A to B ka work done plus work done from B to C plus work done from C to A. But I know C to A is zero. Why? It's an isochoric process. And A to B is a isobaric process. And right, so work done in isobaric process is how much? Integral PdV, right? But pressure is constant. So that will be P into delta V. So this can be written as NR delta T, right? N is given. One R and delta T is 100. That's your work done from A to B. So therefore, work done from B to C will be minus 1000 and minus 100 R. R is 8.314, so that would be like 831 something minus 1831.4 joules. Hmm. Right, Arya. Right, Ishwan. Yeah, because rain, it is a state function, right? If you come back to the same point, your initial and final temperature are same. So delta T is zero. All clear with this? Next one. So this would be a little, mains question on a little higher side, but yeah, it's a mains question. Let's see how they can frame an advanced question. This would be maybe an advanced integer question. So we have a PV graph. We have a process like this, AB. This volume is V naught. This volume is 5 V naught. Here the pressure is P naught. Here the pressure is X times P naught. We are talking about 1 mole helium gas. So when you go from A to B, the molar heat capacity, that is that NCDT में C का value, molar heat capacity of the process AB is 13 R by 6. This is given.
So it's not origin passing, right?
It depends on the X ka value, na?
Mm,
Find X. Question is clear. We have a process A to B. This is not a cyclic process. It's a straight line. But there is no guarantee it is passing through origin. X का value पे depend करेगा. So using this data and the molar heat capacity is 13R by 6. So find X. This would be an integer equation in advance. Try, I'll give you 2 minutes. Reshma, you get a good number. I'll give you an idea. See, again, same thing. End of the day, the story is always about thermodynamics first law only. So dq is du plus dw. Agreed? I know dq is nc delta t, which is tb minus ta. Du, I also know, which is f by 2 nr delta t tb minus ta. Right? And somehow, if you can find work done also in terms of tb minus ta, right? Then tb minus ta will cancel everywhere and you'll end up with this Sika value. So yeah, think about that. Maybe see if you can get X from there. Because end of the day, if you think about this, I didn't teach you anything except dq is du plus dw. So you still have to play around with that. You know, dq is nc dt from calorimetry. And you know, du is f by 2 nr dt from ktg. And you know, work done is nothing but area under the graph. And you know, PV is equal to nRT. So this is the basic stuff. What process, what we are yet to do, all that stuff. So you're still playing with that only. So think. Let's see. Hey, Srihari. Srihari, I'm asking you find X, which is a part of a pressure. How did you even get that thing? Like what you told? Neshman, let's see. So let's get the temperature at A. Let's start from there. One thing I'll tell you, see, generally whenever they give you process, right, if you can actually start with the temperature part, most of the problems get solved. So temperature at A will be P naught, V naught, N is 1 and R. So I know temperature at A. Temperature at B will be X, 5X. Because you will need temperature when you want to find the delta V. So that is also TB is XP naught, 5V naught by NR, N is 1. Perfect. So what is delta U? So UAB will be F by 2 N R temperature difference TB minus TA. F is 3, it's monatomic gas, N is 1, and TB minus TA, that would be P naught V naught by R, 5x minus 1. R will cancel everywhere, you end up with 3 P naught V naught by 2 into 5x minus 1. So that's your UAB. And what is work done from A to B? Work done from A to B is the area under this trapezium, which is half into the sum of the parallel sides P naught plus XP naught by the base, which is 4V naught. So that would be again 2P naught V naught into X plus 1. And what is the heat from QAB? This is again NC delta T. N is 1, and it is given in the question. C is 13R by 6. And TB minus TA is P naught V naught by R into 5x minus 1. RR goes off, we end up with 13 P naught V naught by 6 by 5x minus 1. We are done, right? And then from thermodynamics first law, we know QAB is equal to UAB plus work done from A to B. So bring all of them together, you end up with, you can clearly see P naught V naught will cancel everywhere, so I'll skip some steps. You'll end up with 3 by 2, 5x minus 1. No, sorry, UAB, no? This is 13 by 6, 5x minus 1. UAB will be 3 by 2, 5x minus 1. And work done from A to B is 2 into x plus 1. Yeah, this is solvable. Bring it this side here. 3 by 2 multiply 3. That will be 13 minus 9, 4 by 6. So that's 2 by 3, 5x minus 1 is 2x plus 2. Then bring it this side again here. 10 by 3x minus 2x. That will be 6. 4x by 3 is equal to 2 plus 2 by 3, 3 to 6. That is 2 plus 2 by 3, 3 to 6 plus 2, 8 by 3, 4s are 2s are. Yeah, that looks like x is equal to 2. Or I messed up the calculation somewhere. 13 by x, 3x by 2. So how much was that? There is a 6 in the denominator. Yeah. So the next will be 6. Check your steps. You can't do that, Ishman. You don't know it's a polytropic process. X is equal to 2. Please check your calculations, but I hope you got this thing. If you got this thing, then it is just a matter of solving. Clear how we did this? So I found delta UAB, I found work done AB, and I found QAB, and just kept them in the first law, and then you're done. हाँ समझे.
सर वो 4/6 होगा ना, 4/6 into 5x minus 1.
13 minus. अरे कितना मिस्टेक्स किया रे मैंने. Then what will I get? 2 by 3, 5x minus 1, 2x plus 2. How much is this? This is 10x by 3 minus 2x. That is 4x by 3. 2 आ रहा है ना?
Yes, sir.
2 ही आ रहा है. ठीक है. 2 ही आ रहा है. I did a mistake. Yeah. X is equal to 2 actually. 6 नहीं है. Be careful. Check your calculations. After doing everything, that is a hopeless way to mess up a question. Clear? Next one. Let's do some basic questions. There, get them both. Get them both. Someone got an answer. 3. Okay. The first was easy. So when 20 joules of work was done on the gas, again, be careful with the convention. Work is done on the gas. I don't want that. In a heat engine, you expect the engine to give you work. So here work is minus 40. No, 20 joules of work was done on the gas. So the Q was work done was minus 20. 40 joules of energy was released. I wanted to absorb the heat. It is a heat engine. So heat is equal to minus 40. So if I use this thing, delta U plus work done, so we get delta U is equal to minus 40 and minus 20. That will be minus 20 joules. And he's saying the initial energy. So this is U final minus U initial is equal to minus 20. U initial was 70, so U final is 50 joules. Be careful with your sign conventions here. It's not a tough question, but signs are important. And yeah, some of you did get it. What about the next thing? He said V is equal to KT square. Remember, work done, there's only one formula there, integral PdV. But here you're asking in terms of temperature. So I need to convert everything into, temperature. And we know PV is equal to nRT. So I can write this thing as nRT by V into dV. So I can just differentiate dV there. This will be nRT. dV will be 2 kT dt. That's your dV, and V ka term will be kT square. K cancels, T square cancels. You end up with simply nR integral dt. N is, so this is nR delta T. N is 1, R is this, and delta T is this. So 60. No, there is a 2 also sitting there. So that is 2 nR. 120 R. Clear what we did? Work done is PdV. And if you look at the question, right, he's saying find the work done when the temperature of the gas is 60 degrees, and he's giving volume is equal to KT square. One thing is pretty clear. He does not want pressure in the question, isn't it? That is how you think. There is no mention of pressure. So eliminate pressure. Do I know Vika limits? I don't know Vika limits, but I know DTK limits. So somehow you have to convert everything into temperature. Yeah.
So they should mention ki like the change is positive or negative.
Temperature of the gas changes. ठीक है. अभी दूसरा option नहीं है ना -120 यार. So it is fine. Clear with this? Yeah, I think most of you did get it right. Right, Ovia. You got it. Great. So that's a little about the thermodynamics ka first law. Then let's see the processes. Now, if you see, right, a gas can undergo infinite processes. If you're going from A to B, there are infinite ways you can go from one state to another state. So we cannot study everything. So we will study some standard processes. A gas undergoes infinite, can undergo. So thermodynamics is one chapter, as long as you remember your standard models and the results, most of the questions are actually doable. They're not really tough. So unlike mechanics, right, where you can really twist and ask and everything, thermodynamics, you are actually limited. You can ask, but not as much as rotation or mechanics. So we will study 6 special cases. The first case is isochoric. So the first question comes, when you say isochoric, does it mean dV is 0 or delta V is 0? Which one is appropriate? In an isochoric process, which is right? dV is 0 or delta V is 0? Which is more appropriate? This is a CET question. There's only one option. Now, if you see an isochoric process, right, what do we say? We say constant volume. Right? So think about this. When you say constant volume, suppose if someone says delta V is 0, how will the process can look like? The process can look like this. You're starting from A, you're going like this, and you come back to B. This is a case where delta V is 0, but dV is not 0. The volume didn't remain constant. Initial volume and final volume are same. In this case, the work done, this is not isochoric. So be careful with that. So an isochoric will be the volume should never change. It does not mean you can change and finally come back to the initial state. So this is a case where dV is 0. Automatically, so if dV is 0, delta V will be in this implies delta V is 0. It's not the reverse. Delta V 0 does not imply dV is 0. So if someone asks you what is isochoric, dV is 0. That's more appropriate, not delta. So how do you create this kind of a process? You can take a sealed container, completely insulated. And you can have a heater inside. So you're giving heat to the heater. So heat cannot pass through the walls, but the heater will provide the heat. So this is giving out heat Q. And in this process, let the temperature rise by dT. So when heat dQ is given to the system, so what we are trying to find, we are trying to find dQ, du, and dW in each process. That's the thing. So let temperature rise by dT. Perfect. So first thing, what is work done? Integral PdV. But what is dV? 0. The work done is 0. What is delta U? We saw this from KTG, F by 2 nR dt. Perfect. What is dQ? dq is nc dt. That comes from calorimetry. But what we will do here, since you called it a special process, we will put a symbol C subscript V ncv dt. Getting it? Because you're calling it a special process. For example, if someone asks you, what student are you? If the board exam asks you, what student are you? You are a 11th and a 12th standard student, isn't it? Now, because you're preparing for JEE, we will say you're a 12th student preparing for JEE student, engineering student. If you're preparing for medical, we'll say 12th student preparing for medical. So just because you're doing something little different, we'll give you a special name. So same thing. Since the process is a little special process, we call it CV. Getting it? So technically speaking, CV and C are the same thing. So CV is what? The molar heat capacity at constant volume. So whenever you use dq is equal to ncv dt, it is understood you're talking about an isochoric process. Vice versa. If it is an isochoric process, you can directly do ncv dt. So this is the molar heat capacity at constant volume. Others do keep your cams on. And thermodynamics first law, dq is equal to du plus dw. The work done is 0, so we will get ncv dt will be f by 2 nr dt. So from here we proved that cv ka value is nothing but fr by 2. Getting it? So this we proved, okay? Randomly we didn't get the cv ka value. We actually proved it that cv is equal to f by 2. And if you observe, this is actually constant. For a given gas, f is constant. So cv is constant for a given gas. Is this clear, everyone? So this is the isochoric process. So this is what we are going to do for each process. Any doubts on this page? Clear? Next thing, isobaric process. Again, isobaric process, we are talking about constant pressure. So dP is 0. How can you create this kind of a process? You can take a container with a smooth massless piston. Now, what happens when it is massless? The pressure on both the sides must be equal. Story is the same. The heater will give dq heat and the temperature will rise by dt. So this is P gas, and let's say this is P naught. If you draw the FBD of the piston, this will be P gas into area, and this will be P naught into area. P gas into area. Do you guys remember where else we saw an isobaric process? In KTG, when we did this problem, do you guys remember this problem? This was actually an isobaric process. This one, when you had two pistons connected by a string and you're changing the temperature. So this is an example of an isobaric process. But yeah, any process that is exposed to the atmosphere, right, will maintain this. So P gas minus P naught into area is equal to mass of the piston into area, acceleration. But we know mass of the piston is 0. That's the reason you have a thing. So anytime the pressure will try to increase, the piston will move outside and the pressure becomes equal. So the first thing, what is work done? Integral PdV. But pressure is constant. So integral dV, which is P into, this is V initial and V final. So this will be P into V final minus V initial. So work can be written as pressure into delta V, or you can also write this thing as work done is equal to nR delta T. How do we get that? We know PV is equal to nRT, differentiate on both sides. So PV ka differential will be PdV plus VdP is equal to nRdt. But since the pressure is constant, this term is 0. So you end up with PdV is equal to nRdt. You should definitely remember this formula for work done in an isobaric process. And what is delta U? Same story. F by 2 nR dt. It doesn't matter. You bring any gas, anything, this will be always same because it's a state function. But now be careful here. But just now we proved that Fr by 2 is Cv. So we can write this thing as NCV dt. Now people get confused here. Sir, how can you use Cv for an isobaric process? Again, did I say dq is NCV dt? That would have been wrong. Are you clear? If I say dq is NCV dt, that would have been a wrong statement. Clear? I'm not saying dq is NCV dt. I'm saying du is f by 2 nr dt from KTG, and we proved that Fr by 2 is Cv, which was a constant. So I just replaced it. So be careful with this. So for that means, since u is a state function, so for any process, we can always write du is NCV dt. So you cannot write dq is NCV dt for every process, but you can always write du is NCV dt for any process. But if that looks confusing, just remember F by 2 NRTT. Stick to KTG. Just a way of writing. So because FR by 2 is a constant, which is CV, so we are writing. So it doesn't matter which process I give you, you can always write NCV dt for du only. Clear with this? Any doubts on this page? Then what is dq? Again, from calorimetry, dq is NC dt. But again, since you're a special process, we will call you NCP dt. So technically speaking, dq is NC dt only. So Cp is nothing but molar heat capacity for constant pressure. So if you're sure it's an isobaric process, you can directly write dq is NCP dt. Then thermodynamics first law, dq is du plus dw, NCP dt, du is NCV dt, and work done in isobaric process is nR dt. You end up with Cp is equal to Cv plus R. This is called Mayer's relation. All the story that I told you, isochoric and isobaric process, this is the HSC में 4 marks का derivation. They'll ask you find the Mayer's relation. So then you have to tell all the story of isochoric, isobaric, and then you have to prove this. This gives you the relation between Cp and Cv. And what is Cv? Fr by 2. So you know Cp ka value. So Cv is Fr by 2. So you can write Cp is nothing but Fr by 2 plus R. So if you see in this isobaric process, dq is to du is to dw will be in the ratio of Cp is to Cv is to R. So that is a ratio in which the energies actually get divided. So there was a question like this in mains. 100 joules of heat is given an isobaric process. How much work is done? So du by dw is Cv is to R ratio. So work done will be R by R plus Cv into dq. Du will be Cv by Cv plus R into dq. So there are questions like that. That was one. Then they also asked a question like this. Is Cp minus Cv constant for every gas? They wanted to ask something, but then they messed up asking and they had to, give it marks, bonus kind of thing. So Cp minus Cv is equal to, if Cp and Cv are measured, in moles, then Cp minus Cv is equal to R, which is 8.314 and all that joule, mole, Kelvin. This is valid for all gases. But if you measure Cp and Cv not in moles but in kgs, so if you mess up the units, are measured in joule per gram Kelvin, then see what happens. For oxygen, Cp minus Cv will be 8.3 joule, and 1 mole of oxygen is 32 grams Kelvin. For nitrogen, Cp minus Cv will be 8.3 joule, 28 gram Kelvin. So they're not equal. So just be careful with the units. So if you're measuring that in joule, gram, Kelvin, then Cp minus Cv is not equal for gases. If you're measuring in mole, it doesn't matter which gas you use, it will be always same. So that's the question they tried to ask, but they forgot to mention it is in grams. So they had to give marks for Cp minus Cv is equal to R, and they also had to give the answer when it is in grams. Clear with this? Let's see one simple question on this. If 400 calories of heat is given to a diatomic gas at high temperature, find change in internal energy and work done. Let's get this thing. In isobaric process. That is important. Hmm. Let's see. So du is to dw will be in the ratio of cv is to r, which is fr by 2 is to r. So this is f is to 2. So the catch is diatomic gas at high temperature, meaning there'll be vibrational degrees of freedom. So f will be how much? It's not 5, it's 7. You guys remember that? KTG mein, I gave you that full table. ये टेबल याद है? At high temperature, you'll have extra 2 degrees of freedom. So high temperature mein F becomes 7 for a diatomic gas. You have 3 translation, 2 rotation, and 2 vibrational degrees of freedom. So be careful with that. So 7 is to 2. So work done will be 2 by 9 into 400. du will be 7 by 9, 400. If you take 5, you'll be gone. So the word high temperature is important. Since we have a high temperature, we have 3 translation, 2 rotation, and 2 vibration degrees of freedom. If they don't mention anything, if they simply say diatomic gas, then you take only 5. Is that clear, everyone? Right? And then you can check out the signs. There. Would say you can't get more than 400, right? The next thing, isothermal process. Again, what is isothermal? Constant temperature. dt is 0. Again, this can be created by keeping a one wall of a container conducting, so the heat can go in and out. You can have a movable conducting piston with some mass or friction, it doesn't matter. It should not be massless, or else the pressure also will become same. Now, what happens, because it's a conducting piston, the temperature T0 and T0 will be always same. And remember one more thing, in physics, we always treat all the processes as reversible. Unlike chemistry, where you have irreversible and reversible, in physics, everything is reversible process only. Right? So that means we are assuming every process is a steady state only, almost. So when you give heat Q from the system here, so du will be F by 2 nR dt, 0. Work done, integral PdV. We know this is nRT by V into dV. Since temperature is constant, you end up with nRT ln V final by V initial. This is your work done in this thing. And this thing, right, sometimes you'll get like this 2.303 nRT log. So ln is a base E and log is a base 10. V final by V initial. It is not 1. It is vibrational mode is 1. याद है? I told you vibrational mode is 1. And one vibrational mode has 2 degrees of freedom. Vibrational kinetic energy, vibrational potential energy. So they must have written like this. 3 by 2 kT for translation. 2 by 2 kT for, 2 times half kT for rotation. Plus, they just write kT for vibration. Getting it? And that is because it is 2 times half kT. Vibrational kinetic energy, vibrational potential energy. Clear? So it depends on how you want to write. So we will write like that. We will write it as vibrational kinetic separately, vibrational potential separately. But if you say, no, sir, I will treat the entire vibration as 1, then yeah, okay, then F will be 6 in that case. But then you have to make sure you're writing that will be kT. That will not be half kT. Clear with that? Yeah. So, but again, depends on how you want to treat it as. You want to treat the vibrational kinetic energy and vibrational potential energy separate, or you want to treat them as one single thing. End answer should not change. So, yeah. So if you're taking work in terms of log, so be careful with that. You have to use 2.303, more of a mathematical thing. There have been questions on that also. They gave volumes like, 10 power 3 and 10 square, and then using ln E, you know how to convert that anyways. And be careful, temperature must be in Kelvin. All right, and from thermodynamics first law, dq is equal to du plus dw. So du is anyways 0, so dq is equal to dw. Now, the important thing, what is the molar heat capacity for an isothermal process then? Yeah, you can even write P final be P initial also. So the molar heat capacity of an isothermal process. If you go back to the definition, what is it? It is 1 by n dq by dt. And you're saying dt is 0. So C isothermal is infinity. Understand the meaning of it. No matter how much heat I give to the system, you can never change the temperature. So the heat capacity of an isothermal process is infinity. Clear with this? That's your third one. The fourth one, adiabatic. This is an important one. What's an adiabatic process? dq is 0. That means heat never enters or heat never leaves the system. Means you cannot have that heater. So when you pop a balloon, the air suddenly expands. So you're not giving enough time for heat exchange. So that's also an adiabatic process. When you're talking, the sound waves actually compress the gas. Did you study this in school? Compressions and rare fractions. Sound travels in the form of compressions and rare fractions. It's actually an adiabatic process. Heat never enters or leaves the system. So dq is 0. And be careful with the derivation. Derivation is important because there have been questions where they modify something and you should know how to derive this. So the first law and the ideal gas equation, these two you always have. So dq is du plus dw. dq is 0. This thing is nothing but ncv dt. And work done is nothing but pdv. And we know pv is equal to nRT. If you differentiate on both sides, you end up with pdv plus vdp is equal to nr dt. So n dt will be p dv plus v dp by r. So take this and substitute here, you end up with cv by r pdv plus vdp plus pdv. Bring all pdv terms to one side. That will be cv by r plus 1 minus vdp cv by r. But I know cv plus r will become cp there. So this will be pdv cv plus r minus vdp cv. That becomes pdv cp is equal to vdp cv. So dp by p is equal to minus cp by cv dv by v. Now for convenience, we choose let cp by cv, we start calling this with a new thing called gamma, which is also called as an adiabatic constant. We'll talk about that in a bit. There, now it is just an integration there. So you can integrate on both sides. dp by d is equal to minus gamma dv by v. This would be ln p, this would be minus ln v plus constant. Bring this side, you'll end up with ln p plus ln v power gamma. And you end up with pv power gamma is equal to constant. So this is how you actually derive for an adiabatic equation the relation between p and v. Then you can substitute PV, P is equal to nRT by V. You also have your ideal gas equation. If you substitute here, you get different forms. And you need to remember all the three forms, important. You get a lot of things on that. So the most common thing is this PV per gamma is constant. If you substitute P ka place there, you'll end up with T V power gamma minus 1 is constant. If you substitute V there, you will end up with P power 1 minus gamma and T power gamma is constant. They're all one and the same. You are just playing with that PV is equal to nRT, you'll get all these things. And you should definitely remember this. And gamma is Cp by Cv. And from Mayer's relation, I know Cp is Cv plus R. This is 1 plus Cv by R, but Cv is nothing but Fr by 2. There, this is I wrote wrong, Cv R by Cv. So you can remember gamma is 1 plus 2 by F. This is the formula I would prefer. If you know the degrees of freedom, you can finish off from here. Sometimes they'll give you a mixture of gases. So then gamma average will be 1 plus 2 by F average. And if you see the kinetic energy, right, F by 2 nRT, it's a linear function. So F average will be directly N1 F1 plus N2 F2. So someone tells you 3 moles of helium and 2 moles of oxygen is mixed, you can just use this. You can find F average and then put it in terms of gamma. So mixtures of gamma will be, so you can't take gamma average, don't write like this. Don't say N1 gamma 1 plus N2 gamma 2. That is wrong. You have to find F average and then get it because gamma is not a linear function. And in case you forgot, let me just put down this page again there. And copy the whole thing, I guess. I'll just put a reference there, you can read. Clear with this? Now, how do you find work done here? Now, work done is actually easy. You can say since dq is 0, work done is minus delta u. You'll directly get it from there. But let me derive it also because we are going to use the same similar formula in the next one. So work done will be, I can do that actually. dq is du plus dw. So, and this guy is 0. So work done is minus du. So this is nothing but minus ncv dt. Right? Cv can be written as so gamma is Cp by Cv. You can just play around with this. Cv plus R by Cv is 1 plus R by Cv. So we get Cv is equal to R by gamma minus 1. Replace this. Nr by gamma minus 1 delta T. So Nr delta T by 1 minus gamma. This is one way of writing. And then we can also say Nr T final minus Nr T initial by 1 minus gamma. Nrt is nothing but P final, V final minus P initial, V initial. We can actually skip integration and get this. You could have done integral PDV also. There. So remember these two formulas for work. So work done in an adiabatic process. And this is what I was saying. If you know your temperature differences, you can actually get all the work done. Nr delta T 1 minus gamma. Be careful with that sign in the denominator. P final, V final. By chance, if they give you the pressures and the volumes, then this is the formula. 1 minus gamma. And what is the molar heat capacity for an adiabatic process? The molar heat capacity for adiabatic process is 0. You can change the temperature without giving any heat. So mathematically the dq is 0. So this is 0. Those are also important questions. So molar heat capacity for isothermal is infinity, and for adiabatic it is 0. Clear this? There's a bit of a theory, but that's what I'm saying. You can see all the formulas we are deriving. You need to remember them. If you don't remember them, exam you will slow down. Take a break. Come back by 9:40. We'll continue from here. Sure. Come back in 5-6 minutes. Sure, let's go ahead. So we got PV power gamma is constant. Now, if you try to put this in a graph, it kind of looks like, your isotherm only. So how do you differentiate between an adiabatic process and an isothermal process? So, so let's say I got a PV graph. So this is one, and this is another one. So they kind of look same. If you actually draw them separately, you really can't tell the difference. So the question comes, how do I know which one is adiabatic and which one is isothermal here? Now, for isothermal, PV is constant. Other scams on. Differentiate on both sides. Then you end up with PdV plus VdP. If you remember, we did something like this in elasticity for finding the bulk modulus. Then we get dP by dV, which is your slope, is nothing but minus P by V. That means slope at a point is nothing but the ratio of pressure by volume at that particular point. Similarly, you do the same thing for adiabatic. Here PV per gamma is constant. This will be dP V power gamma plus P gamma V power gamma minus 1 dV is equal to 0. And when you do this dP by dV, you end up with minus gamma P by V. So you can clearly see the slope of an adiabatic process is more negative. What do you mean by that exactly? Negative is great. So whenever I get this right, I get confused like, what do you mean by more negative? Take some numbers. Imagine this is minus 1 and imagine this is minus root 3 because gamma is greater than 1. So for minus 1, what will be tan theta? Theta will be 135. For minus root 3, what is theta? 120. So which is more steeper? So that 120 is more closer to 90, isn't it? So the way to remember this thing is the slope of an adiabatic process is more steeper. So at the same point, the point of intersection, if you draw the tangents, the slope of adiabatic is more steep, means it is more close to vertical. Then if you remember that, then it is fine. So now if you try to draw the tangents here, for the red one, you can clearly see this would be the tangent somewhere here. Let this be theta 1. This is theta 2. Which is more steep here? Theta 1 or theta 2? Theta 2, na? So the green one is your adiabatic. And the red one is your isothermal process. That's a simple way of asking. They can even play like this. If I give theta 1 and theta 2, if I take a ratio of them, tan theta 2 by tan theta 1, and you can clearly see P by V will cancel both the sides, you'll get gamma. So the ratio of the slopes, right? Tan theta 2 by tan theta 1, the adiabatic by isothermal will give you gamma. So you get questions of this sort. They'll give you a graph. I'll say theta 1, theta 2, they'll ask you find gamma. What about this one? Suppose if the graph is, now these two are adiabatic expansions, okay? The volume is increasing in this case, so P naught, B naught. This is an expansion. You can go reverse also. This is an adiabatic compression. Now, which one is adiabatic? Which one is iso? Again, same thing. At the point of intersection, draw a tangent. You can clearly see the red one is like this, and the green one is more steep. So here the green is again adiabatic, and the red is isothermal. So this is how you figure out who is adiabatic and who is isothermal. Clear with this? Important one, because if I give you two curves and if I say one is adiabatic and one is isothermal, how do you know which one is what? And that knowledge is important. And again, it's pure math, the graphs. So if you see adiabatic, right, is a little lengthy. The work done ka formula, the PV per x ka relation, and the graphs. All clear with this? And especially the ratio of the slopes will actually give you gamma. That's another important result. Clear, na, Vedika? Devanshi? Arya?
Yes, sir.
Tanishka? Shreyan? Srihari? Clear? Next thing. That's your fourth process. The fifth one is your polytropic process. What's a polytropic process? So anything which looks like PV power x is equal to constant. Now, luckily, if you see, right, the formulas will look something similar like a adiabatic thing. Here, x is a variable. So this thing actually covers all the process we have done so far. See. So in a PV graph, if I put x is equal to 0, what do I get? If x is equal to 0, then P is equal to constant. So if you put x is equal to 0, you get an isobaric process. If I put x is equal to 1, then I get isothermal process. So by changing the values of x, I can create different processes. If I put x is equal to gamma, I get adiabatic process. So be careful, huh? Meaning if they're at PV power 3 is equal to constant, gamma is not 3. I used to think gamma is 3 and used to do all the problems. It used to be messed up. Gamma has its own special values of 1 plus 2 by f. That x could be anything in that some values become adiabatic. If I put x tends to infinity, then it becomes an isochoric process. So you can actually play around with all the processes. So as usual, first thing, what is du? F by 2 nr dt. So it doesn't matter which process you take, du is always ncv dt. What is work done? Now you can see mathematically this thing looks like PV power gamma only. So you're just replacing that gamma with x and you'll still get the same work done. So P2 V2 minus P1 V1 by 1 minus x or nr delta t 1 minus x. Right? So this is the work done when x is not equal to 1. For x is equal to 1, it becomes an isothermal process. You know the formula. Now using the thermodynamics first law, dq is equal to du plus w. This would be nc dt. Now we are not giving any name. We are just going to call it c. ncv dt plus nr dt by 1 minus x. And this result is very important. So c is nothing but cv plus r by 1 minus x. This is the molar heat capacity for a polytropic process. For different x's, you get different heat capacities. Again, this is a very special case where the process is PV power x is equal to constant. And if you look at the ratio here, dq is to du is to dw. This will be ratio c is to cv is to r by 1 minus x. So this is actually more powerful than the adiabatic thing. You can note down that formulas, you need them. Let me give you a question. Yeah, let's see a question. So helium gas undergoes a process TB cube is equal to constant. Find the molar heat capacity. That's straightforward question. I'll tell you what I did. When something like this came, I thought, okay, this is looking like TV per gamma minus 1. So gamma minus 1 is equal to 3. So gamma is equal to 4. And I did the problem. This is a blunder. This is not an adiabatic process. Are you getting it? X can be any number. In that, certain numbers become gamma. I hope you're getting it. So X is like this. And these values are gamma. It's like gamma is a subset. So every value is not a gamma. So this is a polytropic process. TV power X minus 1 type. So let's see. How do you get this? Right, submit. So T is proportional to 1 by V cube, right? And then we can replace this. So PV is equal to nRT. So PV is equal to 1 by V cube. So we get PV power 4 is equal to constant. So it's a polytropic process. X is equal to 4. You're done. Substitute in the formula. C is equal to Cv plus R by 1 minus X. It is a helium gas. So monatomic Cv will be 3R by 2. This will be R by 1 minus 4. 3R by 2 minus R by 3. That would be 7R by 6. Easy. Again, nothing out of the world. Like that's what I keep saying. Questions will be like this only at a mains level. You should know your formulas, right? Oh, yeah. Clear? Let's see the next one. This is a good one. Let's say a diatomic gas when heat is given to a diatomic gas, in which of the following process temperature decreases? Look at this thing. You're giving heat to the system. And for some reason, the temperature is not increasing, but decreasing. First option, PV power 1.01 is constant. PV power 1 by 3 is constant. PV minus 2 is equal to constant. PV power 1.1 is constant. What do you guys think? When you give heat to the system, temperature decreases. I can even ask a better question. In which process the work done is negative? When heat is given to the system, work done is negative. So you can actually make a matrix matching. I can give the 4 processes here. And then I'll say temperature increases, temperature decreases, work done positive, work done negative. And you have to matrix match. Let's get the temperature. So नहीं श्रीहरि. So the first question comes like if you are giving heat, right over here. That's not the complete answer, Param. There are two answers. So the question comes like this: why is the temperature decreasing? Now, if you go back to the formula, dq is equal to nc dt, but in the question it is given, right? dq is positive, you are giving heat to the system, and dt is negative. There's only one possibility: the molar heat capacity is negative. You actually find these kind of systems. They do exist where you have a negative molar heat capacity. One of the best example, formation of stars are actually negative molar heat capacity. If you give heat to a star, it actually cools down. It doesn't become hotter. It's a weird system. We'll talk about that later on. Advanced revision में करेंगे. If temperature decreases, sorry, if heat is given, if temperature decreases when heat is given, it has a negative molar heat capacity. Meaning, if I had to give a crude example, think of like this. Let's say you have a steam engine there, you're putting coal and you're generating electricity and you're giving it to a refrigerator. The temperature inside the refrigerator ka gas decreases, isn't it? You're providing heat, but somehow the temperature of the gas is decreasing. If temperature decreases when heat is given, so these systems have negative molar heat capacity. So simple. So in these four processes, you need to find who is giving you negative heat, negative capacity, molar heat capacity. Molar heat capacity is negative. So for the first one, C will be Cv. It's a diatomic gas. If I don't mention, I'll take 5 by R by 1 minus X. That is 1 minus 1.01. This is definitely negative. B you can calculate. You'll get positive. C also you'll get positive. D will be 5R by 2 by R by 1 minus 1.1. That's minus 10R. This is also negative. The answer is A and D. Clear with this? The last example, it is just a crude example. It's not even a good example. I'm just saying, let's say if you're burning coal in a steam engine and you're producing electricity. So you're giving heat, right? By burning coal. But if you connect that to a refrigerator, the temperature inside the refrigerator cools down. So even though you're providing heat, that gases inside the refrigerator are cooling down. Something of that sort. Not a great example, but stars are actually negative heat capacity systems. So मतलब ऐसा सोचो ना, when you give heat to the system, right, it is doing so much work, the internal energy is also decreasing. The work done is so much. You're rejecting basically everything like that. So these are anyway, they do exist. So that is one. So that is your fifth process. Now, and these things you should definitely remember the results. Now what I will do, I just put a table. These are all the results you need to remember. You should remember them. You forgot them, then you'll have a problem in this chapter. Like the chapter is quite easy. People, you just need to mug up the things. So you should know the work done, delta U, delta Q, molar heat capacity relation between PVT for each process. You can just have a look at the table. Take a minute. Let's see. The sixth process, the free expansion. So let's say we have an insulated container. Arya, can you keep your camera on? And let's say we have a membrane in the middle. On the left-hand side, we have a gas whose pressure is P, V, P naught, V naught, and T naught. On the right side, you have vacuum. Then what you did, you removed the whole membrane suddenly. If you remove the membrane suddenly, then what will happen? Now, because there's a vacuum there, the gas will try to move. But there is a vacuum there, so there is no one who can stop you. So there is no resistance basically. Now remember, this will be a non-steady state. At this point, right, you cannot define your pressure and temperature for some time. So all these molecules are just moving ahead without any resistance. No one is stopping you because there is a vacuum here. So there is no opposition. Since there's no opposition, then the work done is zero. So dW is zero. And during this process, pressure and temperature are undefined. The gas is not uniform. You can't use PV is equal to nRT. Eventually, the whole gas will get mixed up and everything, and you will reach a steady state. Now, since it is the whole thing is insulated, delta Q is zero and delta W is zero. Therefore, delta U is zero. All are zero in this process. The pressure will become half if the volume is double and temperature will remain same. So in this process, there is no work done. There is no delta Q. There is nothing. Yeah.
Sir, while defining temperature, we said that it's the random kinetic energy of the particles.
Yeah.
So the
Nee,
particles
it is a function of average random translational kinetic energy.
so they will have the average random kinetic energy. So why are
So
they not
question
able to
one, so what is the temperature of the gas?
the sum of the random kinetic energy?
That doesn't make sense. Matlab, the gas is defined in hua. When do you define that? See, let's say in your class, if you make 10 students of 8th standard, 5 students of 9th standard, 3 students of 10th standard students are sitting in the class. What class is this?
Mm,
Nothing. It is not uniform, right?
yeah.
When you say temperature of a gas, you're meaning to say every part of the region should look uniform. That was the first assumption in KTG.
Mm,
Right? The gas is not uniform. You can't define. If you have 4 or 5 different temperatures at different positions, तो फिर भी बोलना है तो you can say I will take a small dB sample and you can define a temperature. You can't say temperature of a gas. It's undefined here. It's not uniform.
sir, but like while we learned temperature before KTG, right?
So that is defined for a gas.
Okay.
So if I ask you this question, what is the average height of a human? 7 feet. Why? Because you have two friends who are 7 feet. So you'll say average height is 7 feet. Average, na? We assume it to be uniform. So yeah, something of that sort. Now, the another way to do this thing, instead of removing the membrane, what if you puncture the membrane? You just make a small hole. यही भी बोल रहा हूँ ना, pressure and temperature of the gas are undefined. ठीक है? It's always about average. Now, if the membrane is punctured, you make a small hole. Now, how is this different from this? Now, when you puncture it, some of the gas will escape to the right-hand side. Now, the right side will not remain vacuum. The moment little gas escapes to the right side, it is not vacuum anymore. So there will be some gas here, there will be gas here. Now, again, this is also pressure and temperature are not defined here. Everything is messed up. So this leaked gas will start opposing. So the gas which leaked here will try to oppose the gas which is coming inside. So this will do some negative work. It's pushing against it, and this will do some positive work. So internally, there is a work going on between them. It's like you're taking money from one pocket and putting in the other pocket. The total money is net change is zero. So leaked gas opposes incoming gas. So dW is not a zero, but the total work done is zero. So that's the difference between both of them. And eventually, again, you will also reach a steady state and you'll come to this state only. So it doesn't matter what you do, whether you remove the membrane or you puncture it, eventually this is the final state. But the difference is this: when you remove the whole membrane, you're not doing work at any instant, but when you make a hole, there's a work done happening between the two gases. But the total work done will be zero. This is your sixth process, everyone. Clear with this? Any doubts on this? There. These are your six processes which we'll be doing. And one last thing, efficiency of a cyclic process. This is important. We use the symbol eta for efficiency. So efficiency is simply the total work done in a cyclic process. By heat given to the system. That is only the positive heats. No, be careful. Huh? You should not take negative heats. Again, what do you mean by negative heats? So negative heats are nothing but the rejected heats. For example, when you put coal in a steam engine, when you're burning it, right? The steam which escapes, the heat which escapes, the smoke which escapes, all this is the heat which is being rejected from the system. You cannot recover them. So if I burn, let's say, coal and I get 100 calories of heat, and in that, let's say 20 calories becomes work, the remaining 80 calories is gone, which is not recoverable. So in a power plant, when they heat up the steam, all the steam that escapes out has some energy, right? You cannot recover it. So in some power plants, what they do, they actually take that steam and they reheat it and they use it. Yeah, it increases the efficiency by 4-5%. So rejected heat cannot be, recovered. So that's how we find efficiency of a cycle. Okay, let's see a question. There, that's it. So if you know the table and you know the process, let's see a few questions on this, how they'll ask you efficiency. PV graph. You've seen this graph before. This is the first graph in KTG. V naught to V naught, P naught to P naught. A, B, C, and D. It's a cyclic process. N is equal to 1 mole. It's a helium gas. So what I want you to do, AB, BC, CA, DA, delta U, the work done, and delta Q. Fill up this table. So for each process, find delta U, work done, and delta Q. And find efficiency of the cycle. There, let's give it a try. Start with filling up the table. So if they ask you to find efficiency, you need to get the table until unless you're sure about certain things. Try, everyone, I'll give you 3 minutes. Fill up the table. And luckily, if you see here, everything is only isobaric and isochoric process. So you really don't have any weird processes here. So try. Give me the efficiency ka answer because you can't tell me the table. Just type the efficiency ka answer. If you got that, then you got everything. You know the formulas for work done, isobaric process, work done, isochoric process. Think. I'll give you 2 minutes, then I'll fill up the table. Yeah. 1/3 of an efficiency. CA in the table. No, CD था sorry. My mistake हो गया. अगर 1/3 efficiency आ गया ना अरे they will buy your machine रे. You बहुत ज्यादा आ गया efficiency. अरे you don't get really that kind of efficiencies. Anyone else got? Nee, Param, that is wrong. 1 more minute, then I'll show you. And you can still keep doing, even after I start solving, because by the time I solve, you'll get another 2-3 minutes. Let's see. So think about this thing. If you want to find delta U, NCV delta T, you need to know the temperature. That is how it starts. So if you know the temperature, everything falls in place. So let's find the temperature first of all. What is temperature at A? PV by NR. So that's P naught, V naught, N is 1, and that is R. Temperature at B and temperature at D both are equal, which is 2 P naught V naught by R. Temperature at C is 4 P naught V naught by R. Perfect. So when you go from A to B, so your delta U will be, so UAB will be NCV dt, N is 1, CV will be 3R by 2, and delta T will be TB minus TA, which is P naught V naught by R. So I can fill up the table here. So this guy is 3P naught V naught by 2. And I also know AB and CD are isochoric process. So work done 0, work done 0. And delta Q is nothing but work done plus delta U. So I can directly add it up. So I got this thing also. It's like kind of feeling like a Sudoku kind of thing. And when you go from B to C, again the temperature difference will be 2P naught V naught. So this is 3P naught V naught. And when you go from D to C to A, it's minus 3P naught V naught. C2D, why am I writing A there? C2D is also, yeah. And then you go from D to A, it's minus 3P naught V naught by 2. You're done. So this guy would be 3P naught V naught. Minus 3P naught V naught. Minus 3P naught V naught by 2. And always be careful. If I add all this, the sum should be 0 because delta U in a cyclic process is 0. Perfect. Then what is work done from B to C? Work done from B to C is an isobaric process, which is an R delta T. So N is 1, R is 1, Tc minus Tb is 2P naught V naught. So that will be 2P naught V naught, and this will be minus P naught V naught. Actually, I can do P delta V. Why am I doing NR delta T? Right, so pressure was 2P naught. And the change in volume was 2V naught minus V naught. And then I got everything. This is 5P naught V naught minus 3P naught V naught minus 5P naught V naught by 2. Perfect. So what's the total work? Total work, add everything, which is P naught V naught. Now in this, be careful. This is your positive heat. This is your positive heat. That means you gave that much heat to the system, and these are negative heats. These are rejected. You cannot recover them. So efficiency of a cycle is the work done by only the positive heats. So that would be to P naught V naught by 13 P naught V naught by 2. That is 2 by 13. Means for every 13 joules of heat that you give to this system, only 2 joules gets converted into work. Everything else is wasted. Right, Samyak? Well, got this. Yeah. Please check your answers. Like, you just need to know the formulas, fill up the table, and you're done. Is this making sense? Yeah, let's see one more like this. Now you guys give it a try. I think you got the hang of it, right? But let's say this is a VT graph. So every time we won't give you PV graphs. T naught, 2 T naught, V naught, 2 V naught. N is equal to 1 helium gas. AB, BC, CA, delta U, work done, delta Q. Fill up the table, find the efficiency. The exact same question, I just changed the graph. Try. Everyone should give it a try. Hmm. Did you guys figure out what processes are this? A to B is which process? Isobaric. B to C, isothermal. C to A, isochoric. So that is the first thing. If you know your process, you know the formulas. Fill up the table. And luckily here temperatures are already given. Once you get the table, efficiency is the total work done by only the positive heats. So the reason why you have to draw a table every time for efficiency, right, is because you don't know which heat is positive and which heat is negative. So if you can figure that out with a table, great. But generally it doesn't work that way. You won't get a good answer. नहीं भैया लॉन में आएगा आंसर वर्क डन आइसोथर्मल नंबर कैसा आया ना if you see B2C is isothermal right you took zero क्या work done try 1 more minute then I'll show you the whole thing let's see first let's figure out the processes. A to B is isobaric. So work done from A to B, I can use NR delta T. So TB ka temperature is also 2T not only. So NR delta T, N is 1, R delta T, that is RT naught. Then UAB will be, it's a helium gas, so 3 by 2, F by 2 nRT, so F by 2 N is 1. That will be 3RT naught by 2. So let's fill it up. So this is 3RT naught by 2. This is RT naught, and this is 5RT naught by 2. I can just send CPDT also. And then when you go from A to C, the work done is 0. B to C, this is 0. So automatically, remember, this whole thing has to be 0. So this is minus 3RT naught by 2. So there's no need to solve. And when you go from B to C, so this will be minus 3RT naught by 2 because this whole thing has to match again. So B to C is your isothermal process. So work done from B to C. Now be careful with the formula here. N R, the temperature of the body, which is 2T naught, ln V final by V initial. N is 1, so that will be 2R T naught ln here V final, you're going from B to C, so that is V naught by 2V naught. That comes out to be minus 2R T naught ln 2. You get a negative there. So this is minus 2R T naught ln 2. And delta Q will also be minus 2R T naught ln 2. You're done. So what is your efficiency? Efficiency is work done by positive heat. So the work done here will be RT naught minus 2RT naught ln 2. And remember, this is the only positive heat. The other two are negative heats which are rejected. So don't use them. Don't add up all this. If you do that, you'll get efficiency 100%. Divided by 5RT naught by 2. RT naught will cancel. You end up with 2 by 5. 1 minus 2 ln 2. Check. I think नीचे you should just take 2.5, right? You should not sign देख लेना. Yeah, plus and minuses. 1 minus right, Utsa, you got it. Clear with this? That's how you find efficiency for a cycle. Any doubts on this, please ask me. And you can see how the questions are. You should know the work done, delta U, and everything for each process. If you know these questions are pretty straightforward. So if you're able to handle this much, I think your first law is pretty decent. But I think next class when we catch up, we'll continue from here. We'll do more problems on this. So chapter is not really that big. And second law, they removed it from the mains portion, but it's still there for advance and bits. So we are still going to do it anyways. So after in the first law, we will also start off with heat engines in the next class. So I think it'll take another 1.5 class. It's a small thing. We'll finish it off and then we'll start with heat transfer. So especially the important thing is all these formulas for the process. Okay, with that, we'll wrap up for the day. I'll see you guys again on Thursday. We'll continue from here. And do remember, there's a test online, so make sure to give. So any doubts, anything else, please stay back and ask, or else you're free to leave. I'll see you on Thursday. So take care, stay safe.